I'm a PhD student at the Institute of Mechanical Process Engineering in Minerals Processing. We have heard a presentation about nanobubbles. To be honest, this is on very smooth surfaces with, which are not opaque. But the scope of the nanobubble session is more about the work at our institute and on the Helmholtz Institute in Freiberg, with or to say they focus more on engineering processes. So we work with rough surfaces that are opaque, and unfortunately we cannot use this technique as you have presented it for us. So some of these applications are filtration, flotation, agglomeration, and we will hear two presentations about results of it and what current challenges we're dealing with. The first speaker is my professor. This is a premiere for me to introduce him. Normally this is vice versa. I've learned that most of you hear some CV facts at the beginning. He studied chemical engineering at the University in Karlsruhe, made his PhD in 2002, joined our institute in 2008, and yes, today's topic is about technical rough surfaces that are present in many engineering processes. He will show us that nanobubbles can highly influence adhesive interactions, and he will show us some models that will or shall describe them, but sometimes they lack. And he will show us some results of our research, a new approach, and the challenges of this approach.
Okay. Thank you, Mr. Chalan. Yes, everybody should have an own professor. Yeah, I'm talking about a little bit going away from the smooth surfaces and going also from the application away from the micro scale. So we are heading forward to real industry challenges, but nevertheless AFM, data acquired via AFM can help us to understand. So we want to clean steel, molten aluminium, whatever you're going for casting. This is our large vessel, this is our large scales, far away from ever what is nanobubbles. But nevertheless, those melts flew through filters like that. And in these filters, small particles are captured. Now we're in the scale of 5 to 100 micron. They have to be removed, otherwise the cast material will be more probably to break, and we get an accident, and we don't want to have this. On the other hand is the removal is better the larger the particles are, so agglomeration is also an issue, so if the particles interact to each other. We see here, we work in a model system, not in the hot metal smelts, but in an aqueous solution where the particles either interact with each other. You see what we are looking at the microscale with the AFM, or they act to the surface of the filter structure, where this is ceramic foam like this. There's one approach what we're doing here, we're applying our AFM. The second thing is on the priority program 2045, we are looking for tailored particles, and tailored particles not only described by one property like size, but also by shape, by composition, by crystallinity, and this focuses on separation those particles from a mixture coming from production, from material occurrence to come to a special defined particle system. And there we apply interfaces like we see here for flotation. This is a Langmuir, and both liquid-liquid interfaces as well as liquid-gas interfaces can be used for selective separation, because they act differently to shape, to size, to surface properties. And this is what we want to investigate. Is there a kind of tool? Is there a kind of difference in property? And again, we can use the AFM. So we go from the macroscopic process to the microscale to understand, to explain, and later on to tailor the properties of the particle systems to come to a separation. So first of all, looking on the particles within liquids, for going back to that, to make them adhere to the surface, to make them stick to the surface, we need to know about the interaction forces. And we got a bunch of interaction forces in that surrounding. So we have, first of all, we are in the aqueous phase. We have van der Waals forces marked here. They are even reduced, influenced by the surrounding liquid. We have definitely electrostatic forces, and then we are now with the DLVO theory, but further on we get some structuring on the water, adsorption layers on the surface. This is, let me say, the familiar bunch we have. But going to the metal melts where we go heading forward to, we get wetting angles which are much above 90 degrees. This is poorly wetted systems, so we have also have a look on hydrophobic interactions. And they are not really investigated neither in science nor in engineering, fully understood, and they can be described by some, let me say, bottom-up approaches, but they are not integrated, not quantified totally. And so we go a little bit to those hydrophobic interactions. There are at the moment two explanations, as we say, in discussion. One thing I think is quite clear. We see here, we got the surface of solids, and then we got a very low surface energy, and the liquid has a higher surface energy. That's why the wetting is poor. The liquid likes to stick to each other, but nevertheless there is nothing in between, so they have to arrange to each other, and this arrangement comes that they have special structuring. We see here there is, let me say, less atoms or less molecules than above here. We got a short-range structuring of the water at the hydrophobic surface, generating an attractive force, because everything which has another surface energy than the surface tension than the water is attracted to that surface. But this does not reach very large, very long distances, perhaps some nanometers, but that's all. But with that, we cannot explain the other effect that we can measure hydrophobic interactions up to 100 nanometers and plus. And here the nanobubbles come to the role. So at the surface, as we have known, there are small gas volumes, and that's not only on the smooth surfaces, but also on rough surfaces. We can see here, this is subject of investigations in the physics, natural sciences, but we're playing in that field, and there are also some approaches looking at an RMS value about 20 nanometers. But if you think of our ceramic surfaces for metal filtration, then we have quite rough surfaces with cavities much deeper than 100 nanometer. And think of a cavity of 100 nanometer for an engineer is perfectly smooth. So rough starts perhaps in several microns. So we're just talking another world, and nevertheless, why shouldn't be there nanobubbles on these surfaces? And are there still nanobubbles? Are they larger? Where are they? How do they affect the interaction? And can we put them in the models we have? Another thing is, we have to see, looking at capillary forces, that the interaction between a surface and an interface, a gas-liquid interface, is always connected to the rupture of this gas-liquid interface, because the solid wants to enter here. This may be with small parts, as we think of the interaction of nanobubbles affecting surface attraction, as well as in large scale, if we put particles into a gas-liquid boundary. So, but now coming to the question, how does describe the particle interaction, how to bring roughness into the game? Are we able to do so? Yes, we are. There are several models because it's a, let me say, a relevant question for engineering. Rumpf started with a quite simple and easy model, which you really can deduct also in a third year course, where you got to calculate the van der Waals forces between a plane, a large spherical particle, and you just take the surface roughness as a smaller particle or a half a particle glued on the large particle, and then you come to a van der Waals interaction looking like this, just modifying the normal van der Waals approach, bringing a geometrical factor in there. You can also use this for hydrophobic interactions, where you use this interaction energy from the hydrophobic interaction. Hoffman modified this a little bit by putting the roughness on the plate side. Okay, going further, there are further models in the market, and looking at the RMS value to describe the surface roughness, doing a kind of integration along the entire interface between a rough particle and a rough plate, or putting a particle between two particles of smaller diameter. All try to describe the certain geometric parameters, the surface roughness. But actually what we get one defined value for the interaction force. And let us look into the reality when measuring interaction forces. Now AFM comes into the game. First time engineers can really get those forces acting on micro level. This is our park system we're using, and this is what we see. There are two things what we can take out of the force distance curves. We got the pull-off force, because we say, okay, that's the force with that the particles are sticking to the surface which we need for the removal. We also could take the energy between, but now we're looking at the pull-off force. Another thing is we can see, not for all measurements, for some measurements, a snap-in, where we approach with the cantilever, and then we get a very fast approach. We try also to resolve this, but this approach is so fast that we just get perhaps 1 or 2 points within the approach. So, and then we see if we map a certain surface, 5 by 5 micron, we see a distribution of the forces. Yeah? And this is the reality. Let us think in distributions. That's we got high interaction forces, middle and low, in the area of 5 by 5 micron, using a 20 micron colloidal probe. And we see the surface is rough, and we see here just the roughness profile. We see another distribution in the game, and the particles we're using are also rough. Distribution leads to distribution somehow. And now we get the results by the colloidal probe measurement. The black curve is the overall force or adhesion force distribution, which covers at least 2 orders of magnitude. This is a hydrophobic system. And if we separate those curves having a snap-in and having no snap-in, we get 2 individual distributions. And we ask ourselves, are with every contract nanobubbles available or not? And as we have seen on the distribution of nanobubbles of surface, there might be also parts where there are no nanobubbles. So that we think we do not have the capillary interaction, which is documented here, in all contexts, and we can distinguish between 2 adhesion mechanisms in the hydrophobic systems. So going further, we see that we have here the hydrophobic interaction all over, but they're much stronger at the hydrophilic interaction. So hydrophilic interaction has the same roughness than the hydrophobic, but the hydrophobic has been coated with a silan coating. And when we put this into relation to all the models I've shown you before, and just take the median value, put it in there, well, the models are different by orders of magnitude, and we do not have one model really fitting to the results and covering both hydrophilic and hydrophobic interactions. Well, large problem in describing the reality, which is now accessible by AFM. So then we got a PhD student until 2 years ago. He looked at that part and said, okay, how can I bring the distributed values to the game? How can I put everything what is distributed, describing by a distribution function, and put it into the model? He went back to the Hoffman model and said, okay, I take this roughness, this model roughness and the surface, and say, okay, I can have a distribution of that, of the radius of this spherical cap, as well as on the angle alpha, how much its has been sunk into the interface. So if a large bubble or a large roughness or a smaller roughness. And from that, I can calculate special values, and I see most of the geometric parameters which I use to calculate the van der Waals force are depending on the size and the shape of this cap. So they're strongly influencing the interaction parameters. With that, I get an interaction force distribution. And let's have a look what is happening. We see here some parameter study where it's been changed the distance A1, which is the distance above the cap. So the long-term efficiency or effect of the interaction force. Here it's the angle alpha, how deep the spherical roughness has been sunk to the ground. You see, this affects the small radii of the particle, and here we get an effect of the large radii of particle. Finally, we come to the point that the measured values we have here in the hydrophilic case fitted quite well to the model. I have to say, we just took not the real distribution of the geometry taken from a topographic measurement. No, it's just put in the log normal distribution for both roughness diameter as well as roughness angle, so how deep it has been sunk to the surface. Fits quite good to the measured data. The next step is, okay, putting the same geometrical approach to the hydrophobic interaction. So we've had exponential decay in here and putting in a lot of geometry in there and taking the hydrophobic interaction by an approach we also heard here today, or some similar approach using the surface energies of the surfaces, which have been generated or measured by surface angle measurements, where we got all the disperse and polar contribution to the surface energy of the materials. And finally, we can bring together the measurements and the model, so we can determine the interaction force. And what we see is we can fit the model to the experimental data, but only to what is without nanobubbles. So nanobubbles are not accessible by the models we have until now for the interaction forces. So, and another thing I like to raise, what is about the precision of all those surface energy-based hydrophobic interaction models. We have here, it's just from a recent diploma thesis from our university, just putting up, okay, having the data, putting in different models. We have one Urs OVRK, so own vent we had this morning, and we get a quite large difference, a factor of 3 between the models. What is the right hydrophobic model? We don't know so far. So the hydrophobic models are not good enough to provide the baseline of the interaction forces, as well as the question what kind of surface roughness we should bring in. Although that's a point depending on the area we are scanning, because we have same order of magnitude scanning area as well as roughness area. So we come with a smaller area to kind of influence on the measured roughness. So finally, some engineering approach to put in to keep in the time. Okay, we have the AFM providing a lot of data. The models are not sufficiently precise to describe the problem. Okay, let us take an holistic and perhaps a data-based approach. Why not only fitting those, and being an engineer, I'm allowed to do so, fitting the distribution, saying, okay, the force distributions we have measured, they can be fit by a Weibull distribution, it's plotted here, the mathematical form, and now I can have a look at the Weibull parameters and see, okay, for the hydrophilic case, B is not relevant. This is going just to an exponential function, and for the hydrophobic part, the parameter B depends on the roughness. And with that, I can predict and use finally in models the distributed interaction force from the hydrophobic. And now containing nanobubbles as well as real structured hydrophobic interaction. And then we can put this into CFD modeling, where we let particles approach to a surface of a collector. This is just a part of the filter, and see whether they adhere to the surface or not, and we get kind of efficiency windows out of this. So we need the knowledge from the AFM, we have to put it into a model to use it in the simulation, and finally to estimate the efficiency. So to come to a conclusion, we have a problem with availability of models. For the simple system, the ideal systems, there are models. They're fitting quite well. The more complex, the more realistic the systems are getting, we have some problems. So we have significant problems to describe this, and the number of models getting smaller and smaller. And then that's the point where we said, okay, on the basis, on the data we have, we should use a holistic approach, just with data approximation, and we can describe finally the problem and make direct use of the data we get from AFM. Okay, thank you for your attention. I'm open for your question.
Have anyone a question? Has anyone a question?
The sorting in the force curves with and without nanobubbles, was this done based on the jump-in or on the extension of the retract part?
The sorting was done on the jump-in. So it's a little bit critical, because actually, but we are sure if you have a jump-in, then there are nanobubbles. But we also tried in other papers to judge by the pull-off force. But actually, there are some events where there's no jump-in, but nevertheless a very high attraction force, because nanobubbles are, gas is growing at the contact point, or the nanobubbles are hidden in the roughness, and the jump-in does not become visible. But that's why the no jump-in curve is quite broad in the distribution. Then we should probably just use another combined technique to identify whether gas volumes are at the contact point.
Thank you. Are there any other questions? Maybe one? Yes. Then it's my turn. I know this presentation, so it's kind of difficult. Maybe a general question. What do you think are future prospects of such models for engineering processes?
Okay, we just have a short answer. I think AFM is one technique which really gives us access to the real forces and the real effects on the surface, especially looking on the colloidal probe AFM, but also cadmium probe AFM is something very interesting. And with that, we can, let me say, improve and challenge existing models, and we have to do it on a broad way, because all the simulation guys are using models from the 60s and 50s, which come from precise work, but nevertheless from a very low databases, and partly for very special systems being measured, and have been generalized in the last 50 years. And that's why in some cases simulations of particle systems are coming to very strange results. So we can use this direct view on the microscale as a new benchmark and a new input to simulation. I think this is a task we have the ability to do for my field in the next 10 years, and to provide better models, better understanding, and this might be also kind of just data-based modeling and just a fit.
Thank you again.
Oh, there is some.
Oh, okay. One last question.
Yes, thank you. It's two questions actually. In this AFM image, do we see nanobubbles or are there none? And do you look at them, or is it just like a...
in this picture, you mean?
Mm-hmm.
No, this is just roughness. Okay,
Mm-hmm.
this is just roughness, but nevertheless, also on those rough surfaces, we are able to detect nanobubbles. But I will shift to the talk of Lisa Ditschelein tomorrow. She will give you a deep insight how to detect nanobubbles on rough surface and to distinguish between topography and bubbles.
Okay, and so I guess we will also be able to learn about the bubbles themselves then by looking at the force distributions, right?
Yes.
Okay, thank you.
Thank you again.